Buenos días. Gracias por asistir a este segundo día del M4Dt Conference 2023. Doy pase a las personas que nos apoyan con la traducción para que brinde información a los participantes que se
Sharing
encuentran.
how we are going to work on the interpretation services.
Adelante, por favor.
Good morning. Buenos días. Tenemos interpretación simultánea durante la reunión de hoy. We have simultaneous interpretation during today's meeting. Hay que buscar el icono del globo en la parte de abajo de la pantalla y escoger el idioma que desea oír. You'll find an icon of a globe at the bottom of your screen, and there you can select the language you wish to hear. La interpretación ya ha sido habilitada. Interpretation has already been enabled. Thank you. Gracias.
Gracias, Keila. Bienvenidos al segundo día de la conferencia anual que se realiza por
Welcome
cuarto
to
año.
the second day of our annual conference for digital transformation 2023. My name is Hugo Casca. Currently, I am the chair of the 14th Working Group of SEAM Metrology for Digital Transformation. I collaborate in Sena, Mexico as the management coordinator in the measurements and for applied statistics. Before we begin with the second day, I want to share with you the following guidelines. First of all, I want to notify you that our event is being recorded from the beginning to the end. The slides and the recording will be available on the website where you registered for this event. Second, we suggest that you keep your microphones and cameras off. And also, you may do all your questions using the chat. And once the presentation block ends, today we will have 2 presentation blocks. At the end of each block, speakers may answer all your questions. So please, whenever you have a question, don't forget to write down who you're addressing the question to. Next, I will give the floor to Ruben Gil, so he may kick off this digitalization block with his presentation regarding the SIM project. Ruben Hill, he's a current coordinator of the Process Task Force for Labs in Group 14, and he works in Acal, Peru, and has collaborated with the digital transformation efforts. Ruben, you have the floor. Thank you very much, Hugo, for your introduction. Welcome to the second day of conference. As Hugo mentioned, I will be moderating this block called Digitalization Projects within SIM. In this block, we will have 3 speakers who will talk about analogic screens digitalization using the imaging processing technique. In these 3 projects, we will see how national metrology institutes and MI, with the intent of being more efficient in calibration processes, they face the digitalization challenge of their measurement tools that do not have analog output nor any other type of interface that will enable them in an easy way to carry out digitalization. Therefore, we only have the challenging and burdensome task of digitalizing the screen. The information will be really interesting and the opportunity to learn. And perhaps this is an opportunity for us. Next, we would have the presentation on the international cooperation project being developed at the moment regarding the design and manufacturing of a barometer, low cost, with digitalization criteria. The idea is to be used in the calibration labs. And finally, we would have the presentation from an Argentinian private company who will share with us how they're dealing with the industries 4.0 industry needs are addressed. Thank you very much for your time. I just want to remind all the participants that you may ask your questions using the chat. And at the end of the block, we will be answering all these And please write down who you're asking the question. Just as yesterday, we want to hear your ideas, views, feedback on international projects and cooperation. If you have streamlined projects that can be developed later using these as a leverage with the NMI. So I invite you to please fill out a form that we will be posting in the chat. So with this, I kick off the first block with the first presentation, software for optical recognition of digital displays, development and validation by Pablo Constantino. Pablo Constantino is responsible of the pressure lab for the physical metrology lab in Uruguay, and he's a representative of the pressure working group for SIM. More than 30 years of experience in metrology, and he has had several scientific publications in metrology, as well as in automation of processes. As for process digitalization, he has developed several original apps regarding chemical and physical applications, which are actively used in different labs. And he also developed the free MSCM Alchemia software for estimating uncertainty by MSN. Thank you very much, Pablo, for your participation in this annual conference. You have the floor. Okay, thank you very much. I am going to see whether I can share my presentation. Can you see my presentation? Everything perfect, yes, go ahead. So we're going to show a project that started a while ago, I think here in Latu, of recognizing digital displays. We used to have a problem with the calibration of forest machines because of the lack of staff. All calibrations are done using an SA2 machine, and it's done at the customer's labs, it's not within our labs. In general, it required more than one person, even up to 3 people, somebody that was operating the machine, reading the pattern, the charge cell for calibration, somebody that was reading the SA machine screen. So through that, with certain movement, it cannot be just stabled. The load, so the reading was done within a specific period of time. So to reduce, say, the demand of staff, what we attempted to do was to build a software that can recognize or substitute one of the operators that is just going to be tracking a number to be able to read it. So that's how several of the conditions that were set forth for developing this application were conditioned under that. It's not that we work with the best displays, we do not work with the best lighting, nor with the best cameras. As you are able to see here, what we were proposed to do was to use the camera that we had, which was a 720 camera, very common camera, rather old, if you will, with normal lighting in a lab without added lighting, and try to recognize the displays available in Lato, however they were in condition-wise, whether old, new, liquid crystal, 14 segments, whatever was available. So we wanted to see whether it was possible. At first, we didn't know whether it was possible to do so. So some device, a way to read any display in an optical manner. And finally, a necessary thing for metrology is to be able to validate the tool, to look for a way, objective way, to see the performance of that application in normal conditions and to be able to measure it in a way that it's duly established and documented. These are some of the displays that we have available. You will be able to see that these displays are to the left for 7 segments. We have 16 segments, the dot matrix, double dot matrix. The last one is a monitor. It's a new equipment that we have, which is like a computer screen. The characters look as if it were a normal display source. You can see the one that says 16 segments, which is a display. That equipment is the tour de force equipment that we have. It's an amplifier of charge cells. You can see that it has several lines and is rather damaged. The plastic that you have on top of those numbers, those white streaks also generate an issue, an added issue to the reading of the numbers. And of course, the source and the numbers are all different. They all have some like slanted, others are having segments in their lines. So that was what we were facing initially. So within this process, we have certain steps that were standard, like capturing, determining the region of interest. Then for those who've seen this, you have to go through gray. You cannot work with colors because the pixel conditions vary. So you go to grayscales first and then binarize it, and finally to recognize the number. So to be able to capture, we use the normal thing, camera of 720. The frequency of the camera, which is the one that came by default, 30 squares per second. So we had a analysis frequency of a photogram every 200 milliseconds, just to give it a little bit more flexibility to the camera's requirements. So this is one of the main issues and problems that we have with people who are attempting to develop this type of applications, and is how we recognize the number that we want to read. There are displays that have several inscriptions. There are displays with pattern readings and the samples from the calibration. There are other displays that have time, temperature. So the software cannot decide unless we tell them what we want to read. Though they can recognize all the characters, it is impossible for them to know which is the one that we want to read. So this led us to make our first decision to determine the region of interest manually, to put on the cursor and tell the software what region we want to read, to create a box saying, this is the number that we want, and the app should read that one. See, this phase also entails to straightening the numbers when they're in italics, to correct the spin of the camera or the equipment, or that we were not able to locate it or position it horizontally. So we didn't want to do it at the hardware level. So we just wanted a common support where we can modify the image within the software itself to spin it, or even change the perspective. When we see it from the side and it's larger, the image is larger, the closer it is to the camera, to keep the numbers as rectangular as possible so it is easier to read. So here we're facing a problem that took us a long time to solve, and it's that deterioration of digital displays. So you can convert an image in grayscaling, that's not difficult. languages do it right now with easy functions. However, the scratches when they're too large or the wear and tear of the display, it's difficult to read under the grayscale. So the combination of colors, just the way they are, cover it or adds an added streak due to a scratch or something that was meant to be read as a 2, it reads like an 8 or a different number. So these things need to be foreseen and taken into account beforehand. So we propose ourselves a strategy that perhaps is the most novel thing that I can share with those who wish to learn about this type of application, is to first to do the color binarization. So over here, we could see the filter, and then I will explain this. The filter application come from Python. So this display has a worn area where the 0 is. It's covered. Regardless the filter that we use, it's still covered. However, there is a difference between converting from grayscale and separating colors. Oftentimes we see that an equipment has the display, the numbers in red, and the streaks and scratches are colorless. So if you first do a color binarization, the colors the way they are, from 0 to 255, and say in IT, colors are composed by 3 colors, red, green, and blue. So if you take a threshold instead of just using the grayscale, such as the one that is here, the one that is separating the grayscale in 2, which would be the 2 color peaks, the number and the background. So here we'll separate what is underneath the red becomes 0 red, and what is on top of the threshold here will be 255. And that's what we did with all the colors. So here, instead of having binarized in gray, what we will have is 8 color combinations for gray. One that is comprised of all the colors in 0, others in 254 yellow or blue, sorry. So this will be different combinations within what we can do. So this will enable us to separate the different display characteristics. So in this display, which is the one that had the previous filters, you can see that over here is just separating in grayscale. So this is a modification that we did of the software to analyze this recognition aspect. That's why we see the graphs next to it. So it has a natural division that you would do whether you're separating the background from the numbers, and you can see that scratches are visible. So whenever we do a prior filter in color, see, you can see the RGB. The first color is filtered, but then it is transferred to grayscale, and you see that the scratches at the far left, the worn area is white and the numbers are gray. That's because there are different channels of the 8 that I mentioned. If you separate all those channels from the different color combinations, you will be able to separate. This way, if we only leave the channel, which that's the channel 3, which will be the light gray 4 numbers, we can see that it completely disappears the visual notice of the wear. This is a very efficient way to be able to filter physical scratches of the displays. So finally, in the processing of the image, there's several other ways filter this. We already have established filters in the different programming languages. So at the end, we chose those sliders that the software had so we could actually create the threshold manually. So by now, we are modifying that so it's more automated. And this first one that we were showing, we were still doing it manually. And over here, we have another decision that we needed to make, whether we were going to use ODs. Here are the ones that we have, TCA, or we would do it differently. So it didn't convince us. We've seen other experiences using OCR. The performance wasn't good. So we tried to do it in a more creative way to be able to determine the numbers. We're going to explain it here. So there are two ways. Numbers are different. The seven segment displays have obviously 7 regions, which are the ones that are required to be determined. The rest are not useful. These are all the ones that are highlighted in this 3 times 5 matrix. You can see the amount of pixels that you have on whenever we digitalize the image, what is black in the image. So if you see that it's on, you select it as 1, and if it's off, 0. So that sequence would create that sequence screen. For each number, you would have a different screen, and only comparing that result with the predetermined templates, we could see what number it is. So what we need to do is to separate the numbers into these pixel squares and to directly count the pixels. We count how many pixels in each one of the boxes that represent a segment of all the 7 segments, and to determine what the combination of both, what is the number. None has 0. That's because of the noise of the image is never perfect. The cleanup of the number is not perfect, but it's easy to determine what are the ones that are on or those that are off. The other option, specifically for other types of displays that are not 7 segment one, but the 14 ones, or the monitors or sources, is to do a 5 by 7 matrix instead of 3 by 5. So the principle is the same. You count the pixels, but in this way, given that it's more demanding, the level of precision. So what we do, or what we really do, is to look at a percentage of similarity with the template that corresponds to the number. So we read the boxes that are on off, we put it on that screen, and then we compare it with the matrices for all numbers. The one that had the highest percentage of matches, that's the one that wins, and that would be the one that will be selected to determine the number. So we had a minimum similarity of 30%. So if it does not find any above 30% in similarity, then it will not have a reading or a result. So this is a little bit about the boxes for in real-time digit. This is a binarized matrix 1. You can see that it's a 4, but it doesn't have rounded edges. It doesn't have a perfect definition, but that's what we get from the image. And we need to take into account that if we read every 200 milliseconds a photogram, all photograms for one number is different. It's got noise, it's got differences around the edges. So each program needs to have their own analysis. And this has some additional problems. For instance, the previous column for analysis purposes or determining the number box, it would seem as though the number ended. If we have an 8 and is divided by half, on the right could look like a 3. So you need to take those into account. Now, the images are not perfect, and the count could be different, can vary. And at a specific moment, we need to determine the percentage of how many pixels are on per square and what is the percentage that we're going to consider as enabled. So this is based on looking at all the results that we have for all the counts. Finally, we go to the validation phase. What we did was to build Arduino, and we have a display for 7 segments. These are 8-digit randomized and all 8 digits. And the idea is to make it as demanding as possible with a sequence of digits every 1 second. And the minus sign, random. One of the numbers will have a negative minus sign. And the randomized point that could show up throughout the sequence. So what we did is to read that number sequence by the series and independent from the camera and with a software to be able to keep it on to compare the number of sequences, so the person wouldn't have to decide nor count or write on a piece of paper, and to eliminate human error during that assessment. So both numbers will be the same, the one that is shown in the display and the one from Arduino from the series, and the comparison is done with the software designed for that particular purpose. So over here we have a first prototype from the first test. I put it here because it's really interesting, because the equipment that we used is not the one that was used for validation purposes. This is a Fluky device, which are rather complicated to read, so it's not easy to differentiate the background because of the reflection. The green number would be what they're reading. So this is the image and the green number, the reading. Somehow I cannot make it play. So this would be the validation phase. So over here we have the statistics of the hits and misses. You can see over there, these will be 1,000 sequences that were read, the number, the total. So the performance is 99%. So it's also interesting the time that it took to do the test. So we have 2 of the examples, the one that we got the best result from with 33 seconds, 2,000 sequences. Let me see. Okay, yes. 18,000 digits, but in 33 seconds, none were picked up. To the right, both readings, the one from the series and the reading from the camera.
A ver. Pero bueno, no todas fueron tan buenas.
Not all of them were excellent.
Acá tenemos
So over here we have
uno bastante malo,
a very
con
poor
57
reading
minutos
with 57
y
minutes
23 errores.
and 23 errors.
en esta imagen se puede ver, buscar en cuál fue el que erró. Yo lo puse ahí en el video a ver si se ve. No. A ver. Ahí está. Bueno, no se ve. Pero a veces son diferencias en lo que no leyó nada, porque a veces es en el refresco digamos, de la secuencia de dígitos cuando el mismo display cambia, que la lectura la hacen esos del cambio y de repente lee mal. También hay problemas de iluminación. Nosotros observamos que todos los errores, digamos que da muy bien durante mucho tiempo y después cuando empieza a fallar todo el tiempo. O sea que hay como diferencias de iluminación o algo que puedan afectar, pero en general tiene una bastante buena performance, siempre está por encima del 99%, por lo menos el de lo que obtuvimos hasta ahora. Bueno, muchas gracias.
Gracias, Pablo, por tan interesante exposición y felicitaciones. Te pido, por favor, si nos puedes acompañar durante el bloque para responder las preguntas de los asistentes.
Por supuesto, por supuesto. Gracias.
Bueno, continuamos. Ahora tendremos la siguiente presentación que lleva como título Reconocimiento de caracteres aplicado en la lectura de LCD de dispositivos de mano, la cual estará a cargo de Isaac Ruiz. Isaac Ruiz es ingeniero electrónico egresado de la Universidad de Panamá, involucrado en proyectos de investigación informática durante sus primeros años profesionales. En 2014 pasó al sector privado como consultor y desarrollador de software. Desde el año 2021 forma parte del Instituto Nacional de Metrología de Panamá, el CENAMEP, con el cargo de metrólogo en el área eléctrica y apoyando los proyectos de transformación digital y automatización. Por favor, Isaac, adelante con tu presentación.
Vamos a hablar sobre el pequeño desarrollo que voy llevando
So we're going to look at the character recognition applied in reading LCDs of handheld devices. First of all, the background. We have a certain amount of equipment that we use, equipment that we don't have the communication interface all the time, and this represents more work among metrologists. We are highly trained. We have highly trained metrologists, highly trained personnel. But we need to take better advantage with the maintenance of the measurement standards in order to be more efficient. So in 2020, there was the idea emerged in order to calibrate these devices as part of the project with improvements that were made. So the proposal was, first of all, for the application to be adapted and so that it be more efficient regarding time use based on open software to reduce the costs and facilitate maintenance and improvements. Mainly the extra expenses were for licenses, and it was also to facilitate improvements. So this is why it was decided to use Python, because metrologists in the center, we already had experience with Python. So the objective was to maintain an interface, a graphical interface, user-friendly, and for centralizing, to manage the data in a centralized way, that is the database, either a local one on the computer or storing it on servers. So this is the diagram of the project blocks. We have the three main ones here. Data acquisition, first of all, responsible for obtaining the data from the camera and carrying out the transformations of the video frames. Then we have the validation module to make sure that everything is correct and based on the database. And the final module are the control elements, the thread control and the graphic interface. So through these blocks, it's a thread control without affecting the data processing and not affecting the time period. Also, in this block of program development, we included the work table with the camera, the illumination. So here, there was a very good initiative at the beginning using a camera in color. So we were able to facilitate the process in this manner. And we can see here the images of the work area, specifically in the laboratory, where the frequency is assigned. And we can see the user graph here too. So the graphical interface was developed to make it more visual and user-friendly. And to the right, we have the image, and on the right, to the bottom of this graph, this is what we used as a detection. And on the right, zooming in, we can see the tools and everything that we need to do prior to running the test. The pre-processing option, the bilateral filter, and this facilitates the work a great deal. Another thing that we can program as well is the LCD numbers, if we want it in black and white, and another type of filter that we can enable for transformation. We can also select a model. It can be a tesseract. And then under validation, we can program the number of digits. In the capture module, we have, first of all, the frame extraction. And this leads us to to be able to cut the area of interest and then make any adjustments necessary. To make it brighter, for example. And we can regulate these aspects. But the main problem are the reflections. But we can solve that using light rays and using what we call the reflection angle under calibration and the camera. Then we have the morphological modifications, which is to extend or reduce the number of pixels. And then we use the Tesseract OCR and the timestamp. So it's an advantage to be able to work in this way, in a modular way, and have the Tesseract OCR and use a verification method. And we've been looking at that option. And finally, we have the time stamp to determine the single time for this capture. And we can keep each of the images that we capture and that we analyze in a folder. All of this is done continually, constantly, and it depends on other elements. We work between 4 and 12. In the evaluation module, we have the data, first of all, the data queue, and all of the information that's generated from the extractor. We check this data, and we make a digit evaluation, first of all. In the case of Tesseract, it's necessary to evaluate the digits to make sure that the decimal point evaluation is correct and eliminate errors. For example, 0 to 0. This is the type of to avoid problems in this area, and so that we can recover the information, we analyze them and then go on to the next point. Sometimes it's not possible to recover them because in that case it's because we don't know what the source is. So then we have the decimal point evaluation. And we do this because we have to program it for extracting the data. And this is something that we determine prior to running this evaluation. And then we make the error evaluation to determine the percentage of error. And if the percentage is too high, then it's rejected. Because it could be that the equipment is maladjusted, and so the errors are superior to the permissible percentage. It's important to determine the database that's going to be used as well. If it's going to be external one, or if it's going to be an internal SQL or an external management database. We can also generate reports here. Regarding evaluations for verification, if or rather, we used a configuration determined by the computer, which was standardized, and we carried out this calibration, the equipment calibration, optical character recognition, and this was acceptable. So the error level was at a low percentage, so an acceptable one. So what we did here, we took a number of samples and saved them for different types of acquirement, different values too, or different types of acquisition, the acquisition window in seconds. And here we obtain the percentages. We did this conversion by hand. We took these percentages and compared them with the values. Most of the time we did have 100%, but interesting was with this reference frequency of 500, the percentage was 83%. And we can see the errors here. I apologize, but he has a lot of echo in his microphone, and it's impossible to understand everything he's saying for interpretation purposes. So this was the level of rejection and the times. We're going to watch a video. This is the reading of values using OCR. In the laboratories, these were screen reading tests using the tachometer. We can see here the work area and the camera. It's a professional camera being used. Here, we're taking the data, collecting the data, and you can see how it's advancing. In the second case, we're going to see it in laboratory E4. We're using a more economical, a cheaper camera. It's a web camera, a webcam. Using the reflected light from the light source. And you can see the difference in the images here. But we're also capturing information from the screen. And here we can see the process. We created the experiment here so that it could be saved in the database. We decided on or selected the type of equipment, the tachometer, the values, and the unit. the period and the number of samples, the time interval between each capture. So we determine all of these details and the filters too. We can determine the increase and the range, and we can select reporting here too. It can be manual. We determine the area that we're going to read. And we can make modifications here. The decimal points here. And the model that we're going to use, the form of analysis that we're going to use, we can determine that here. So this is the method for determining the points that we're going to analyze. And this is just for general information about the temperature, humidity, and the stabilization time as well, if we're going to include that. And also in the program, we can add these points. If it's necessary, we can have the calibration point. And in the program, we can also extract the values and report them on Excel, for example, or elsewhere, depending on what we select for the extraction. So this is how we use the program. So the results, well, we managed to run the program, and the performance tests had errors lower than 0.05. We made a comparison of the reading, comparing humans and machines. And when they're done by humans, it was within our expectations, and it's a functional application. In current and future work, right now we're working to implement E4 multimeter laboratories and HO, that is reading controlled climate cameras, with a sufficient space on the video screen. And we're also adding certain improvements to this. Specifically, well, we often analyze 2 or 3 devices, and we have to select the area of interest for each capture. So I admit that there was a delay on my side because I was supposed to add certain elements for generating the signal. So it's important to include these values. And we are working on improving the evaluation process, or detection and evaluation, based on meetings with the working group. And so we're involved in that work, in developing improvements. So basically, that's it. Thank you very much for your attention. And thank you for the invitation too. Thank you, Isaac, for your presentation. I would like to ask you to remain until the end of the block in order to answer questions from participants. Let's continue with digitalization of displays of measurement instruments. And now we have a colleague, Carlos Galvan, who will present considerations to develop an OCR for electronic displays. Carlos graduated in IT and a postgraduate degree in IT and industrial mathematics in the Mathematical Research Center, CIMAT. He is the head of a group in the longitude department in the National Metrology Center of Mexico, the CENAM. He's also responsible for graduated rules and optical machines of coordinates in CENAM, applying development methods on algorithms and digital processes of images for longitude measurements. He's developed different software for measurement instruments, such as an interferometer of standard blocks, the graduated scale blanks, geometric adjustment, and many other applications. Right now, he's coordinating the group of digital certificates, calibration certificates of CENAM, and he coordinates the DCC group of the working group 14 of SIM. He's also a technical coach in the Cabaret project on visualization in the SIM. So thank you very much, Carlos, for being here today, and go ahead with your presentation. Thank you very much, Ruben. Could you confirm if you can hear me well? Yes, we can hear you and we can see your presentation too. Thank you very much, Ruben. Thank you, everyone. Thank you, the committee as well, for having invited me here. And to conclude with this block related to OCR, the optical detection of characters. In CENAM, we do have some experience in this area. I don't want to just show you anything in particular, but what I'd like to show you the experience in general that we've had in the center when carrying out this kind of activity. As you observed, it's not just a question of using algorithms for detection, but there are several other steps that need to be taken that are also important in developing these applications. So I'd like to show you some points that for somebody who's interested in developing OCRs, take into account for developing them better, for facilitating the process. So what are the main elements for an OCR system? Obviously, the image acquisition hardware, and we've seen several examples that colleagues have been using, and that's a very important part. Another important part is the illumination. Some have already mentioned illumination as an element that's affected the detection of or characters or character recognition. It's an important part. And finally, of course, processing software that's based on processing algorithms with artificial interference. Let's go on with the next slide. Thinking about image acquisition hardware, there are several possibilities here. It could be through a digital camera, as was shown by some other colleagues. They've been using digital cameras, but the problem there is that you have to take into account the cost. Normally, they're very expensive, these cameras, and it's not just necessary to have one camera, but it's also necessary to have the necessary equipment for improving the focus or the image interval for the captures. One suggestion, one idea is to adapt a webcam because that costs less, but we have the problem of the signal and noise relation there because of the quality. We, for example, in recent months have been using a cell phone. People might think, well, a cell phone is very expensive, but we're not thinking here of using a new cell phone, but rather an old one, and updating software and one that we don't use for communicating anymore. And I think that with this, we can take advantage of the circular economy concept. So we could use an old cell phone for capturing these images that will allow us to communicate and have the image on the cell phone, transfer it to the computer, and it will be a good quality digital image because the cell phones normally do have good cameras, and they will allow us also to zoom in, and also these can be recognized by different systems. I would like to emphasize the illumination system now.
It's very important for OCR lighting. Over there, we saw some examples of how lighting can affect us, and I believe that those of us who've used a camera, we've noticed that it's different to take a picture in a room with no lighting than outside. So lighting in general is very important. So the effect of lighting does impact on recognition features. So it is important to have a lighting system that improves image quality. It could be a system that we obtain from a different tool that we can be exchanging to see whether we can actually use it, or it would be an entirely new development. In the electronics required for this is quite large, and now we have a lot of things available that we can develop in a more simplified manner at a low cost. And well, we can purchase one, but we have to think about the versatile cost. Isaac mentioned that you can use all these light rings used by YouTubers, a light ring, and it's really cheap when you use this type of tools for lighting. But it is very important to consider a lighting system within our own general OCR scheme. We should not lose sight of that. We do need to take into account for including it. Perhaps in some areas it won't be necessary, but try to encompass all these applications that we can do. It would be rather important to take that into account. And very much finally, we reached the last part, which is software for character recognition. So we're going to see some, which are the most known ones that have had the best results based on statistics. But I wanted to focus in several steps prior to that. It's not just necessary to have a software for character recognition. As a matter of fact, the examples that we saw before the examples that we had from Pablo, they do a pre-processing before delivering the image to the image recognition program. Therefore, it is very important to have pre-processing, processing before delivering the recognition image. Then we have text location. Perhaps the image that we're going to deliver has around something that we can locate. So we need to indicate where that software is to be more efficient. How do I identify each character? And based on the examples that we see, it's not just all the word, it's done by character. So it is important that those characters are duly aligned. So you can try to avoid mixing two characters within the image. So afterwards, we do this through patterns and a post-processing at the end. What do I refer to post-processing? Here we have an example of an image of OCR that's directly captured in the first image. I have noise, specker noise around the image. So that could make it complicated for our algorithm to detect that, especially with binarization schemes. And so it is very important to align the development. So a first step, so perhaps I can use filters or any other type of Gaussian filter to eliminate. In the second image, you can see that that image is already filtered, that we don't have that noise. It could be of best quality. Afterwards, we have the contrast improvement. I must make sure that my image has a proper contrast. It can discriminate clearly all characters from the background, from everything that is around this. So it could perhaps be a better management of imaging program or any other tool that increases contrast, brightness to improve the image quality for my recognition software. Another type of pre-processing that we could do if it were required, of course, this will depend on the images that I'm recovering, it's thinning. I don't want to deliver an image that is very large or thick, but I want something more fine or thin. And for that, for instance, I can use some of the morphological filtering, like dilatation or erosion to thinning it out. Right now, we have removed the noise, improved contrast, and we improve erosion to improve this. So over here, I will show you an example of how we improve the pre-processing. In the first image, this original image, where I want to recover 12-14, and this has something in the background noise, background contamination. If that image is sent for processing to look at the characters, it tells me that it cannot clearly detect the character properly. So what happens if I start to apply this? For instance, the first thing that I do is that I apply this cleaning or filter. We have the image where the characters 12-14 are white, and that's where I apply the threshold, and then I can see the image with the highlighted characters. And then I apply a filter which is called distance transformed image. That is to say that I'll try to isolate or join the characters or the adjacent filters, the elements that have some noise. I'm going to eliminate by applying this distance filter, the threshold distance. I will have an image where we could see 12 and 14, the fourth image, where we only see 12 and 14 and very little noise around it. At the end, we have applied the threshold. I will be filtering now each one of the numbers, and then I will be fine-tuning the image, improving the quality. At the end, I applied the opening filter, a morphological filter, and then I obtain in a clear manner the 12 and 14, and perhaps some edges. And finally, I apply a mask to remove elements like text location to eliminate noise. So it's not the same, the image that I have at the first image. They are different with the last one. It's clearly better defined. And obviously, if I send this element to Tesseract or any other software for character recognition, the result could have a higher level of accuracy. So this is the important part of pre-processing. We obviously need to find the pre-processing space. So these steps apply for this image. But these elements we can leave it for another type of processing. This is an example of 1214 applying the mask, and at the end we only have the final image. Okay, so finally the next step would be text location. So for that, the tools such as OpenCV, they have tools for text location. However, here there is a compromise. To detect characters can be requested in real time. To add detection, image detection takes up a lot of time because the algorithm needs to analyze all the image to see where the text is. So there is a compromise here, whether it's worth the while to be done with the software or it's best if I do it, indicating the areas that I want to detect. So that is your decision to see which is best for your application to do it either manually or using software. So it is very important the time that it will take to do this. And at the end, we have character recognition. And for that, obviously, there are several softwares. But I believe that given the approach that is too general, it may have certain errors. That's why we have had other apps such as EasyOCR or Keras or Paddle OCR. Paddle OCR, as a matter of fact, is a recent development, not 5 years ago, and it's public. And I've found that it has a lot of support. We have fora, blogs where they're discussing this, and it's an ongoing improvement. As a matter of fact, Paddle OCR is the latest tool that we've been using. We've already used Tesseract, Easy OCR, but now we've decided to use Paddle OCR for character recognition. And this has given us really good results. If you Google Paddle OCR, you would get a lot of information. It is compatible with C and Python in different settings, which facilitates the integration to the different development settings. So finally, some comments. The algorithms that we're showing, these are generic algorithms. We need to take that into account. They are thought for solving not just the detection of displays, but also the document detection. As a matter of fact, they're focused towards that to digitalize characters on documents. So we need to be very careful that the adjustment that we do for a digital display is the appropriate one or similar to the one that we have to get better results. For specific cases or with a lot of problems with the screen type of denomination, what we can do is to do some training. I can have a set of images with real values, and thus I will train the algorithm to get the best value. So when we've attempted several phases of processing with different algorithms and we do not get the appropriate results, what we can try is to create our own image sets with real and correct values, and then we give it to the training software to improve. So some OCR models in the cloud are focused on PDFs. So here we need to take into account that these OCRs, that's why we still haven't had really good results using these tools, because they're focused on documents where the contrast between the character and the background is very clear. It knows that it's just characters. So when we see something that is not character, then we see problems, noise, and it starts to join characters. So mindful with this, we need to consider these elements. And also we have to take into account the image size. Given that they're focused for documents, the image size that I deliver is important. If the characters that I hand in, they're very large, I would think that the higher the resolution in my image in my camera, it would be best for OCR, but not necessarily it will apply for these type of algorithms, because a very large character for it, it has no relationship, no match, because it does not match with any of the protocols that it was used for its definition. So this is some of the things that we've been doing. We're using now Paddle OCR. We've created now the lighting system using ring lights and control bars. So this is what has rendered the best results. Perhaps somebody who wants to train on this, AlexNet. It's a framework for neural networks that allows for the training and easily to train the algorithms. So this is all I have for you. I know that questions will be left at the end. So I am at your service to be able to address any questions. Thank you very much. Thank you, Ruben. Thank you, Carlos, for such an interesting presentation. Certainly, all of us who are starting to develop this type of system, this will be very useful. So please, can you just stay at the end of the segment for Q&A from our participants? Thank you, Carlos. Okay, so now we have Aldo Garcia, who will give the second presentation, the deep scene on the development of a barometer with digitalization criteria for the calibration labs. Aldo Garcia has experience in developing projects and services for vibration and acoustics in Senam, knowledge applied to measuring acoustics, calibration experience, and the enhancement of measurement system for instruments and different transductor services. And he has knowledge on programming and standards for uncertainty measurement, team building, ongoing improvement of agile models, implementation. He actively participates in digital transformation for Industry 4.0, Metrology 4.0, calibration, remote sensing, and metrology. He's leading one of the working groups for digital transformation within SIM under Agile projects. Thank you very much for your participation today, Aldo. You have the floor. Thank you, everyone, for the opportunity to present this progress, this type of report that I wish to share with you today. On the SIM BIP project, and it's associated with the thermal hydrobarometer development, THB. So I wish to start by mentioning that we have a series of participations in the SIM region where we have several countries that are participating actively in the development of this project, where we have Argentina, Costa Rica, Peru, Chile, Mexico, Ecuador, Brazil, and special collaboration with PTB in Germany. And we also have the presence of coordinating groups where we are liaisoning the development of this project. As a summary of what we've been getting during this project, we've carried out more than 50 technical meetings. All the stakeholders, technicians are working day in, day out to review the project's progress. And we want to create 5 demos, a demonstration where we're going to show all the progress of our project, because we have to meet certain specifications and criteria. Up to now, we've had 2 virtual meetings since 2020 up to 2023. We have an in-person demo that we held last year in Panama. We have a virtual demo meeting in October of this year, and for November, another one in Paraguay to show the final product and to submit and deliver the product to SIM. So up to now, we have had 2 standardization workshops for THB, where we invite all the members of our group to participate, and we can share the step-by-step of how to integrate certain solutions to the hardware and how they can use certain tools so they can have this environment condition monitoring systems. So up to now, we have 5 devices following the proposed specifications within the project, and we have had expert meetings with meetings with experts in temperature, humidity, pressure. We've done 2 surveys listening to criteria and experience so the project can deliver a device that can be useful in labs, in most of the labs, calibration labs, for environment condition monitoring. As for what was proposed, we've achieved 90% of the project thus far. We still have a 10% remaining before we deliver the final device, and we have really good progress. And we worked with agile models with incubator projects in SIM, where we define the project scope. We also have defined the features that make up this component, sensors, process integration features, and they all have a deliverable at the end of the project. So whenever we add all of that, we'll provide the scope that we have visualized to use hardware with certain features, to have calibration protocols, the integration of hardware to be able to get the device to include all the required tools for the metrologies at the lab with communication options. And then we're generating a web app that will enable us in the future, near future, to have the facility to be able to validate the entire system and do comparisons. So, as was mentioned, the development is a low-cost device for measuring environmental conditions, temperature, relative humidity, and pressure, and also to manage information. As was mentioned, we use an agile model, and we have a well-defined structure of who are the members and elements of each one of the areas responsible of developing the features. So each group using this methodology has been self-sufficient, self-managed, and it has held its own working meetings to reach all the mentioned objectives. Specifically, each one of the groups, for instance, sensors, has already proposed a calibration protocol where they mention calibration points and they review the uncertainty sources, and they've proposed a calibration method, for instance, of the different types of sensors that we currently have. We've studied each one of them to see which one renders the best results so they could be better integrated into our labs. And the proposal is to follow steps towards calibration. So within process feature, we have a scheme that visualize all the components that make up the hardware of the environmental conditions hardware system. Everything that will create and be the composition of that system, a screen with information storage, date time, including warning and registration of situations that are undesirable, or to have an alert of something that is happening with our measurements, and to have the capacity to have different communication channels so labs may have different types of different labs with different technology maturity can communicate. And also, we've identified each one of the operation intervals depending on the magnitude and also the type of controller sensors. I've already mentioned this. So that device itself can be replicated in case an NMI is interested in developing this environmental condition system. Also, we have the integration of XML as a way to transmit information. This is to integrate CMCs as a type of the PTB scheme, where we're also integrating the digital unit international system within the PTV. And this will help us meet the objectives of digitalization proposed for 2024 and the following years. So we're developing this device so whenever it's in a more mature phase, it could be integrated without any issues. And in the part of integration, we are also developing this web application that has SQLite data management and information management through MQTT. And this app is being developed to be able to connect different devices, which are the THBs that are being developed, and thus establish a monitoring network system where we can integrate several of this in one area and to be able to monitor them and to be able to review them online. So this app also may be used to configure the same device, to do hardware adjustments, and to monitor and visualize the measurements results that we are getting through these. So as you are able to see, the objective of developing this system, this device, will open the doors for labs, at least in environment condition monitoring may have proper control of data and information, and then they can integrate that into their calibration processes. That's why we focus on being keen on what our colleagues are doing in the lab, to listen to their opinions, and that all problems that may arise, for instance, whenever they integrate the systems from other brands, and that they need to adapt it to these ones and cannot be updated. For instance, over here, we could have an advantage that it could be configurable, the system itself, and we can update, because precisely that's what we're doing. We're creating it within different metrology centers with the best features possible to help metrologists within their own labs. Up to now, as I mentioned before, we have 5 devices. However, if we visualize that we have 6 that already have a prototype that is operational, we are thus in the standardization phase. So all features that have been defined in the implementation meet the criteria that we previously defined. We're right now at the phase of those 6 to only have 1 device that is operating. And for that, we have to improve a few things that we still have to develop. But at least I wish to mention that, for instance, here, Mr. Sepúlveda Espinosa from Sename Panamé, Cristi Sanchez, and Isaac Ruiz from Colombia. We have Carlos Peña, Edwin Culma, Costa Rica, Olman Ramos, Senam, myself, Inacal, Ruben Hill. So I want to mention specifically that these are the names of the people who have developed these prototypes that you see. However, I know that there are more colleagues who have been contributing with other prototypes, and there are also being influenced with these projects development. So of course, there is a group behind all of this, and each one of the NMIs that I just mentioned. So we need to add the name of all the people who have been supporting, to a certain extent, the development of these environment conditions measuring devices. So we need to keep on running tests to be able to deliver the best version at the end, at the beginning of November. That's why we need to calibrate the system. Right now, we're doing this calibration. Each NMI will do their own calibration. I am here right now in Germany, and I want to see whether they can verify the THB that I brought here We're reviewing the performance with connectivity. We're looking at the MQTT integration. We're designing PHTB to deliver a solution. We are looking at the design of a case to protect the entire device. So you cannot see the raw components, but they're all contained under one case to validate the device. We're going to generate manuals and guidelines. And we're also reviewing the process in case of technology transference when interested NMIs wish to apply this. And this is how we will be better able to transfer technology without any issues. And at the end, as I was sharing before, we're going to make the most of the annual meeting of SIM, which will be held in Paraguay in November, to also carry our final demonstration meeting and to deliver these devices physically to the representatives of the SIM. And also we're going to hold a presentation before the industry, the secondary labs that are interested.
In the SIM meeting to show the product that we've developed with the interaction of the members of the Inter-American Metrology System. And we have plans to present this development in 2024 as well. We've been invited to make this presentation in MECA 24. So, looking to the future and having communication here with the PTB, we're developing systems that are machine actionable. What we're trying to do is for the systems, the measurement systems, to be able to integrate artificial intelligence and take advantage of all of the infrastructure of digital certificates, of the International Digital Unit System and digital standards. And I'm saying that, well, in a few years, this will become a reality, in fact. But we would hope that next year we can continue in that direction so that the HBs can be used, or the THBs can be used to be machine actionable, and they can be automated, and not just that, but smart. And we're seeing how we can propose the next phase of this project for upcoming years, 2024 and 2026. So thank you very much for your attention. I'd just like to say that, well, we are willing to answer any questions and hear any comments, and thank you for your attention. And I'd like to thank everybody who's been participating in this project, because the work has been excellent. So thank you. Thank you, Aldo, for sharing the progress with this very interesting international cooperation project. I would like to ask you to remain until the last presentation of this block in order to answer questions from participants. Thank you, Aldo. So if you do have any questions, you can put them in the chat and also indicate who the question is for. But to close this block, we have Cristian Mucio. He will give the next presentation, Traceability in the Measurement of Vibrations in the Context of Industry 4.0, Achievements and Next Goals. Cristian is a chemical engineer. He graduated in 2006 and a PhD in engineering in 2016 from the University of Buenos Aires. He got a master's degree in strategic and direction and technology from the Technology Institute of Buenos Aires in 2022. He's been working since 2006 for high-tech, and he is currently the manager of research and development. He has developed different measurement equipment with physical variables and their integration in platforms for predictive maintenance and optimization, analyzing data using artificial intelligence, as well as NIR spectrometry equipment based on detecting the concentration of product in equipment for detecting color and concentration. He also has publications in scientific reviews, international ones, and he participates in projects, research projects funded by the national agency. to promote science and technology. It's a privilege to have you participating in this event. And well, the floor is yours, Christian. Good afternoon, everyone. Thank you very much for the presentation. I don't know if you can see my screen and hear me well. Yes, we can. Well, good afternoon, everyone. Thank you for having invited me to participate. On this occasion, the idea is to talk about a project that we are developing with INTI. The project focuses on incorporating in the chain value, into the value chain, the new technological tools, in this case the DCC, to get a better solution for the final user. As you can see here on the agenda, the idea is to introduce the company, but I know that we're short in time, so we're going to summarize this and talk about the project that we're working on and that we want to develop for an ecosystem to achieve efficiency, comment on the progress that we've made in this project with INTI, and then next goals. To start with then, I'd like to describe rapidly the company, High-Tech, started over 35 years ago with a mission to provide technological solutions that add value to productive processes for our clients, based on mainly on the analysis and control of the significant parameters of these processes. High-Tech started 35 years ago and focusing on research and development as the basis of its competitiveness. Since 15 years ago, we have a formal department of research and development where we carry out innovations, both hardware and software ones, and research lines. One of the research lines is related to technology for industrial non-invasive measurements, and another line is related to technology related to 4.0 industry, which is a line that I'm going to focus on during this presentation. Also in our department, we have technologies such as DCC that we're developing, and this is we transfer these to other departments such as the metrology department. The metrology department has the purpose of responding to an internal need of other areas, and it became a strategic line since 2019. It's been in the Intersect network, and we started working together with a new measurement capacity and calibration measures, and developing aspects related to DCC and its integration into calibration. This work is being carried out with part of this project that I mentioned before, and it covers the specific project that I'm going to be discussing. So quickly, the project, the objective that is the equation of sensors and the development of a platform based on the cloud to continue using the information from these DCCs obtained from the calibration system. The idea is that the calibration system that we're developing can issue these certificates, the DCCs, with traceability. And for this, it's necessary to integrate the software with the calibration instruments, the commercial calibration instruments. As you can see on the slide, the particular objective, this is part of the general objective, and that is the design of the use of the DCCs within the framework of 4.0 industry. As you know, then there's a path towards 4.0 industry, continues of the data context, and so that based on these data we can get information and then analyze and transform this information into knowledge, which will allow us to generate prediction models that will enable us to take action, and the final aim is the optimization of the processes and products. One of the derivations of Industry 4.0 is to maintenance based on conditions, predictive maintenance. And this is where we've focused our development over the last 4 years, approximately, through the use of different technologies, or enabling technologies, including big data, also the Internet of Things, machine learning. And the project has required the development of these technologies, but this is like well, this is one of the most important characteristics. And the incorporation of DCC is crucial for industrial measurements. So in order to obtain the maximum use of the data, we had to develop hardware and software so that these could be integrated. And in order to integrate the different enabling technologies of Industry 4.0, the ecosystem that we developed is made up of a series of sensors here on the lower left, and the acquisition device for processing data that then are sent to the cloud. Then they're calibrated by a calibration system, which is the one that we're characterizing. And a DCC is issued that is stored on the cloud and with the vibration sensors. So related to this development that has progressed through an associated project to the DCC. So as we thought at the beginning, the DCC is associated to the vibration sensor and will be stored on the platform to be able to analyze uncertainty. It also allows us to know the status of the sensor and its long-term operation. And this has a significant impact on the value chain as far as the final user, which was something that was mentioned earlier. Furthermore, it will make it possible to guarantee the traceability of the missions, the veracity of the data, incorporate the possibility of exchanging sensors, improve predictions involved in this knowledge and the knowledge of the measurement of the uncertainty. I'm not going to spend too much talking about the development of each component, but I wanted to mention that the data in the vibration sensor, there's a pre-processing process for obtaining the relevant information and sending it to the cloud for subsequent analysis. This pre-processing in real time, what this enables is the incorporation, or rather the increase of security, data security, and with the information of over 90%, and that reduces the resources necessary for storage in the cloud for subsequent processing. Once in the cloud, the data are used for taking action, obviously. So we have three components in our chain. The first one is a vibration sensor. The second one is the acquisition, and this is used for monitoring the condition of the assets. In our case, the sensor, we call it T sensor, and the capacity has a capacity to generate the data in three axes. Here we can see an installation of the sensors in the field. If you look at the image on the left, the sensors have been installed, and on the right we can see a T sensor and a hand sensor more or less in the same position so that we can make comparisons between the different measurements. Quite clearly, both devices should be in the same position or a similar position. One of the things that we saw specifically when we used this equipment in the field is that one of the main sources of variability in the measurement of vibrations is the positioning of the sensors. Because of this, we had to develop a kind of anchor, a sensor anchor, to allow for repeatable reinstallation and for maintenance, taking into account maintenance of the sensors. In addition, the position in this position, we have the platform for getting information specifically related to sensor orientation. This allows us to verify, to see if the sensor has moved. The second hardware component is the edge computing, this T-box. This was tested in INTI, and the image that you can see here, this was in a test of a 30,000 volt discharge test to see if it could support this level of discharge, and the design was tested. It's quite a strong design, and we were able to pass all of the tests of electromagnetic compatibility. The last link in the chain is the platform. Once the data from the sensors reach the T-box, then they're sent through the MQT platform, the platform that receives them and stores them for subsequent use. In the cloud, the pre-processing is carried out of the data through different algorithms that have been loaded, and the purpose is to be able to deliver to the final user valuable information that will allow them to take action. Most of the users don't have the knowledge or the time to interpret everything that's generated, so it's necessary that the platform provides a diagnosis autonomously and sends out different alerts for a deeper analysis. So this is useful for harmonizing data from different sensors, for detecting anomalies, for evaluating statistical control rules and other aspects. Here we have a screen, and we can see here the different assets. So quickly then we can observe the status of the asset, and if we want to go into it, we can click on an asset and see its status. If we click on status, then this takes us quickly to this screen where we can see the evolution and the variables here in each risk indicator in the period being analyzed. Without going into too much detail, the platform also includes a screen. The users always require this, and this provides a possibility of exploring historical data using different tools. Here, what we can see is a spectrogram, and here we can see the possibility of evaluating different spectrums in different proportions. The platform also has the possibility of sending reports to users. Here we have an example of a report with one of the graphs that we saw before, and we can send warnings through text messages too. But as we said before, the value of the information, the results and the alerts issued by the platforms would be much greater if we could ensure the veracity of data, the status of the sensors and the uncertainty of the measurement. Furthermore, even though it's true that the market of predictive maintenance requires local sensors, this is a requirement for calibrations. What we've observed is that they are more useful for guaranteeing the velocity of the measurement and also for making comparisons with sporadic measurements using manual devices which are used for this type of maintenance. So a couple of years ago with INTI, we started this project to incorporate data from the calibration of sensors to the DCCs. This information is available for guaranteeing all of the sensors and the uncertainty of the measurements in order to incorporate the effect into the detection and prediction algorithm. The idea, to summarize, is to generate, or the DCC is generated and stored in the cloud. In the first place, we need to characterize a shaker. This is an internal vibration standard through a calibrated standard, and we control this so that the conditions of the calibration can be used for calibrating our sensors, and in this way issue a DCC that will be stored in the cloud and associated to this specific T sensor. Last year, well, we summarized the status of the project and we commented that if we had the software for the DCC, we'd acquired the platform for this, and that not the platform, sorry, but the equipment for calibrating the sensor in order to generate the processes related to the standards and the equipment acquired. We needed to characterize the equipment in order to calibrate the T sensors and adapt them to the platform for use of the DCC. This year, we progressed with several areas. You can see some of the equipment they acquired and some of our own development, such as the anchor of the shaker and other things that we had to do for issuing the DCC using the shaker. And you can see that with the red arrow And we had to characterize the internal standard and the authorization of a standard by INTI, which is what you can see with the yellow row. The results of this characterization process showed the correct line between the amplitude generated and the tension measured using the Endevco versus extension generated to measure the tension, and this was informed by the manufacturers together with the sensitivity too. So here we studied the variability of the tension at different frequencies, and we can see here in the graphs that there was some variation, and in effect there's been an effect. If you carry out a more detailed analysis, you can see that the variation is minimal. Then, after characterizing the shaker, we used it for the first tests with the T sensor, and we constructed an additional piece for the shaker, and we carried out several measurements with the T sensor. And in this case, you can see it here in the graph, two different ones, and the idea was to continue with this measurement of the amplitude and then progress with calibration. We also tested the T-sensor using a verificator for verifying sensors in the field. This is for the process of the user. And then we made a process with adapting the platform for DCCs. We carried out tests with the DCCs for this and we uploaded the files in a readable, machine-readable and a person-readable format. And in the screen, you can see a list of 4 certificates for 3 different sensors. The first 2 lines are for the same sensor. One is active, and the other has been archived and linked to the active one. The third line shows that there's an active certificate that is about to expire in October. That's why the expiry date is in yellow. And the last line is a certificate that was rejected by the user because of an error, so it was dismissed and it cannot remain as an active one. If we look on the right here, under actions, we've got 3 options. We've got the control, we've got looking at the certificate, and the third one is the configuration of this record. So if I click on this last one, I can configure it, the certificate record, the status, the validity period recommended. If I click on C certificate, view certificate, I can see the information with the data that is legible by people. So most of these have been concluded. You can see the different colors there. And the final project status with in full color the current status. There are just some that need to be analyzed still, the T sensors and the use of the DCC. And to conclude this presentation, then I wanted to mention briefly our upcoming goals. First of all, a finalization of the calibration of the T sensor, and for this we need to conclude the characterization, then an inter-comparison with INTI to determine the correct calibration of our sensors and the procedures for these calibration. Furthermore, we'll progress with incorporating a functionality that we've been working on, which is the automatic evaluation of the status of the sensor and the next date of calibration. Here we have the 2 charts that we're incorporating, and one we can see the sensor, the comparison or main points, error trend, and the comparison with last known calibration. And here it's possible to know if the sensor is out of tolerance or if it's necessary to modify the calibration period. And finally, the development of a new VT sensor with several improvements. It's going to be lighter, which will result in better measurement characteristics. It indicates its status, and it will have an improved anchor for facilitating calibration in the shaker. So that's everything that I wanted to tell you related to the incorporation of the DCC in our platform in Industry 4.0. I hope it's been interesting, and thank you for having invited me to participate. Thank you. Thank you, Christian, for this very interesting presentation. I'd like to ask you and the rest of the speakers to turn on your cameras so that we can start this short block of questions and answers. In the chat, you will be able to see a link to a form, and I want to ask you to fill out that form. If you could do that during the morning. And the idea is to collect your information about the cross-cutting projects related to digitalization and automation, so that we can share this in the SIM community. So meanwhile, let's go on with some questions that we have. This question is for Pablo Constantino, and it's related to a slide where we could see the pixels being counted. How have you reached that conclusion of 5%? Have you tried with more pixels, maybe in order to improve detection, or how did you reach that value? Well, we started initially with the 7 segments 3.5. The thing is that the segments, if we think about a number 7, the 7 would have the LED on and the 2 laterals on the right, but there's a lot of equipment on the 7, so we'd have to look at the point matrix, or the ones that use sources, and so the 7 has the vertical signal, which is oblique. And this cannot be read. So here, a lot of this has this element, this 5%. So the 5%, this number emerges from the point matrix. There are some displays that have more points because the matrices are larger, but it doesn't really contribute to anything. And we do get good recognition with this level. The larger the matrix, the more difficult it is to make an analysis of similarity with a template. Thank you very much, Pablo. The next question is for Isaac Ruiz. Isaac Ruiz. He wants to know which laboratories have implemented this and if there is a value related to how much has been the reduction in time between a manual system and a semi-automatic system. Thank you for the question. First of all, we have implemented this TC1, and we're looking at implementing it, that is implementing 4 for calibration. We need to separate things, however, the time of the procedure, because the time is based on the procedure. And there, what we have is that the user is involved directly in taking the data, or is no longer involved in this, so they can use that time for other activities. So what we're looking at is to achieve a time use, to improve the use of time. I don't know if I've answered the question. Yes. Thank you, Isaac. Here we have a question for Christian. If you could say more about the DCC that you're implementing, formats, and if you're using XML and the scheme that you're using for this. Yes. Thank you for the question. It's a very interesting one. In fact, we are using as reference the structure proposed by the PTB, and so this is an XML DCC format, and associated with this XML file, we upload a PDF. So we have the computer readable part and also the human readable part here. So that is the structure that we are using. Good, Christian, thank you very much. And we have a question for Aldo about if for the second stage, then that you mentioned in one of your slides, if you've considered taking other magnitudes that could be considering environmental elements such as vibration and electricity tension. Yes, in fact, we've thought about the part of acoustics of generating this type of device for environmental noise. And of course, I think that these do already exist in the area of electricity, but would be interesting to develop low-cost possibilities for monitoring these variables. But I can confirm now for acoustics, for our environmental noise, we are thinking about developing this, yes.
And the last question is for Carlos. And they ask us regarding OCR, have you seen or are you using or other institution is using deep learning? Yes, thank you, Ruben. Yes, as I was telling you, we are using the network for training some display algorithms. And we are training the networks using this model based on deep learning with neural networks. So we're working with more prototypes. Okay, Carlos, thank you very much. So we have finished this block with the Q&A. Thank you very much to all the presenters. These were very interesting, up-to-date topics, and they will be very useful to all of us who are working in the area. Thank you very much, Pablo, Aldo, Isaac, Aldo, for this wonderful presentation. To participants, yes, thank you. Participants, please can you fill out the survey? You can do that during the break that we're going to have. And based on the program, we're going to have a 15-minute break. And afterwards, we're going to look at the last block of the day. We're going to look at tools for the next steps in digital transformation, which will be moderated by Rodolfo Sousa. So this is everything I have for this section. Hopefully this has been a very good block for you, and you have the form there to be able to share your opinion. And with that, we close this block and we go to the break.